in Farfetch products, and I define how I'm going to store each one of the documents in my database. And then you have another pipeline in which you receive your query. You also define how do you pre-process your query in order to define how are you going to match the pre-processed query against your list of stored documents, and then have a matching, and hopefully the information that someone is trying to find with the query will be in this pool of documents that you receive at the end. If you have any questions, feel free to raise your hands and I will answer it live, basically. And this is basically a really simple diagram that will get us through all the journey. So, but let's just roll back a little bit and try to understand, in a typical search engine, what happens, for example, at Farfetch when I type in the search bar the query address. So on the backend, I probably have something like this. So my user wants address, and somewhere in my list of products, I have a shoe and address. So I also have a bit of information around each product. For example, I have a description. And in this case, I will try, for example, to match the query into the long description. And for example, in here, I found dress. So I'm able to say that the user wants this item and he doesn't want this item. So this is a great success. So I did my first information retrieval answer. Basically, when you have two items which are pretty similar, what happens is that both items will have, for example, the word dress. So they will both be retrieved. But what happens, for example, when you search something like red dresses? So if you search for something like red dresses, you could have a match which would be something like this. So you have the word red in here, but what the user searched for was dresses and not dress. So those two items would probably not be retrieved. And this is a problem. You can see right here what you basically do with these pre-processing steps is that you try to find a way to solve those kind of things. So a really common thing to do in this pre-processing phase is something called text normalization. So basically, when you receive something like red dresses, which is basically a string, you need to define a way to divide it in much smaller units of meaning. In English, it's pretty simple. So I have red dresses, I have a word which is red, and I have a word which is dresses. But in other languages, for example, Chinese, in which you have different characters and each character combined with different ones mean different things, it's much more difficult to establish this type of rules. And then you can also establish linguistic rules in order to, for example, if I receive something in a plural form, I send it to a singular form. And in this way, every word that I have will be in a singular form, so they all will be retrieved and I will solve this problem. Most of these techniques are mainly based on work from linguistics teams. So basically, there are a lot of matching lists between words and, for example, lemmas of the words, which are the roots, or do simplifications of removing suffix and prefix parts of the word. But there are also really cool papers around the area in which you can do this using natural language processing and neural networks, but I don't want to get much into that in this phase. So basically, you have a way to make the text more uniform and basically solve the previous problem. And when someone, for example, searches for red dresses, it can also match on the backend against the word dress. And basically, you also, on the matching phase, you can establish a lot of intuitive rules to sort the items out. So you basically can say that if you have a big list of documents, you can say that items with a term should have a higher score. So if I have boots and I have dresses and I'm searching for dresses, the dress will match against the dresses. So if the query I'm looking for matches against the document, I will retrieve that document higher in the list. You could also say that the field where the match appears is also important for matching. So imagine, for example, at Farfetch, each article, and this is just a random article, you can have, for example, the brand name, and then you have a long description around the product, and then you have like a short description, and then you have, for example, composition, and then you have the color, and then you have where it was made. So basically, when you are trying to you are basically trying to have a score function around this. So you will have imagine that someone searches for dresses, you are going to match it against every single field, and then we'll calculate the score. So, for example, it would be much more likely for the item to be relevant if you match again, for example, a short description than a long description. The probability of having noise in here, it's much bigger than having noise in here. Basically, the relevance of the words also depend of their commonness. So basically, what this is saying is that imagine in a long description like this one, if you pick up all of the words that you have in your documents, those that show up the list are more relevant for the product. So for example, most of my products will have the word for or the or and those words, for example, will show up a lot if you search for those specifically words, and all the documents would be retrieved, but they are basically noise. If someone searches for red dresses and white shoes, I don't want to receive all the products matching with and, for example. So you basically are saying that words that are least frequent, for example, the word dresses is much least frequent than the word, for example, and, so you should give a higher weight to that word. So in a really simplistic view, what you do is basically you have a formula that defines how this matching is done. So you say, this word does a match against my document, and you have it in multiple fields, and also the words are not that common, so this product is probably relevant for what I'm trying to do. And then, if you have a really big list of documents, you score each one of the documents, and then you define, okay, below this value, you cut them all, and just show the rest of the products. And that's basically how a free text search works. So each time, for example, someone searches at Farfetch, you can basically, we go to our backend, and in our backend we have, for example, 2 or 3 million products, and you match the query against all the products, calculate the score, and then define, okay, below this score, the query normally isn't relevant, so they don't have that type of information don't show up. Basically, going back a little bit to this diagram, we can basically try to see different ways in which you can enhance your information retrieval system. So you can define more complex pre-processing. So you can say, for example, that this document will pass through a pre-processing phase in which you reduce all the words for the singular form. But you can do a lot of things in the middle. For example, you can say that if the query, for example, golden shows up in here, you also map it to a synonym, for example, yellow. So there are a lot of things that you can do in here to try to enhance either the representation of your document, so give more information to the document, and also to the query. And then you also to keep in mind that you have a really big index, so response time is really important. So optimizing the way in which you store your information is also an area of study. So there are a lot of cool algorithms that you can look at to map and to build these inverted indexes. Then you also have the matching phase. So you need to define what would be the most suited way in which you match your query against your list of documents. For example, if I'm searching for a dress, it would be incredible it wouldn't be relevant if I try to match it against shoes, because in the backend I may have somewhere in which I categorize each item as the type. So I can say that the dresses are part of the dresses category and shoes are part of a shoes category. So I could try to make a match against those type of fields with a much higher relevance than the others. And then you also can have optimization on this side. So you can define, for example, if you are showing more or less documents. For example, at Farfetch, a listing page may be really big. So you may be giving back like 200, 300 products. And even if your needle is there, the user may not even see her, because she may be like on the bottom of the pile of documents. So you could also optimize the way in which you sort those items. Ideally, for example, you could have also after this phase, implement a lot of business rules. For example, you don't want products without stock to show up because persons will like that product, but they won't have stock, so they wouldn't buy. So in this pipeline, there are a lot of things that you could optimize, but a simple information retrieval system goes around all those phases. And to give you a quick example, for example, this could be a way to start the inverting index. So basically, you would count the occurrence of each word, and you would count in each document where does it show up. You would sort them by alphabetic order, and you could retrieve it much faster. So I will give you a quick example of how those type of things also affect Farfetch, and how did we, yes? Yeah. But not necessarily for the same user on other places. We don't do it, but you can try to, for example, do something more personalized in which you look at, since you are looking at the distribution of users that already use Farfetch and search for similar things, you could do some things around that. But in this case, we are trying to look it in a more naive way. So forget the, let's just say, you can look at the previous queries from other users to optimize the queries that you expect to receive in the future. Not necessarily in a more personalized way in which, okay, that user already searched for that, let's present him more things around that. In this case, what you are trying to find, it's a different way to basically discover your list of products. For example, if you search for red dresses at Farfetch, you will have something like 10,000 results. So, and in this, with a big catalog of documents, you will end up with a lot of noise. So in this case, you were just trying to sort it out, but without having the personalized information of the user in account. Okay, so going back a little bit, so imagine, for example, an example at Farfetch. So you have something like what I just show up in place, and then you search for something like golden shoes, and then you end up with a Farfetch page like this. So you search for golden shoes, and you receive black shoes. So this is us when the product told us, oh, I searched for golden shoes, and you guys are showing black shoes. So what's going on your side? And we were saying, okay, everything is fine. That's the expected behavior. And basically, one of the product owners told us, well, I want you guys to find me the golden goose with golden shoes. So I have two words, which are basically the same word, but they are used in different contexts. So golden in this case means, it may mean a golden goose, so literally a golden goose, but it may also mean that I want something from the brand Golden Goose. And in this context, golden shoes means the color. So they are the same word. In the pre-processing phase, they would be exactly the same. And when I retrieve it on the other side, I end up with black shoes. And why? What? Sorry. Did I jump the slide? Let me see. So it's the 30. I misplaced that slide. Sorry. Okay. So there are a lot of ways in which you can look at this problem. So basically, you look back at your diagram and try to see, okay, where can I correct this problem? So should I give more information to the documents? Should I give more information to the query? And all those options are valid. So I basically can define, okay, I'm going to give more information to the documents. This way, this information don't show up. So if someone searches for golden, it's a synonym for the color yellow. So yellow will also be matched, and the things from yellow will show up higher in the ranking. I can try to understand the query better. So I could say, in those contexts, golden is a color, and in another type of context, the golden isn't a color, it's a brand. And I could also say, okay, it is something on my matching side, so I'm giving more relevance to matches in fields that they shouldn't happen. And what we found out is that, for example, in our long description, when you searched for golden goose, this black shoe, this is a black shoe? Yeah. Yeah, this is a red or, green shoe. Yeah, this is probably a green shoe, but this shouldn't show up. And why is it showing up? Because you have golden, so golden matches here, and then you have shoes. So according to your information retrieval system, this is a really relevant item to the search. And as this type of things, you have a lot of ambiguities in search. For example, you could want golden shoes from Fendi, and in this case, you know that golden is a color. And in this context, golden goose is a brand, so I want something black from golden goose. And even with really simple queries like red dress, you may have, I want a red dress from Gucci, or I may want a white red Valentino dress. And if you preprocess it only, you would end up with pretty similar results, when in one case red is a color and the other is a brand. So the main idea and what we ended up attacking is query understanding. So we wanted to understand better how to understand the user query. And the main idea was to give a meaning to each sentence. So each word is basically have a meaning depending of the context. And at Farfetch, I may even have a way to associate that meaning with a specific, let's just call it entity. So I know at Farfetch that the item has a brand, and a brand is different from a color, and it is really different from a category. And I know those specific meanings are specific from Farfetch. So ideally, I would be able to sort them out in some way, having also in mind complex patterns of information. So there is a vast record around natural language processing in ways to do those kind of differentiation between words. And I will present you a little bit about the work around our hierarchical deep learning natural language parser for fashion. And this is a lot of keywords, which is really relevant when you publish something. You need to hit the right keywords. Unfortunately, you don't have machine learning there, but you have deep learning. So let's go back to our main quest to find the golden shoes from Golden Goose. And what we end up building was something like this. So each time we receive a new query from Farfetch, we end up being able to classify as each word as a meaning, let's just say, an entity. So this may be really complex, but I will sort it out really quickly. So ideally, I receive a string, let's just say golden shoes from Golden Goose. I find a way to divide it into words. I do something which I call it here word representation. Okay, I pass it through those complex models, and then I end up with, for each word that I have in here, with a categorization. So golden in this context is a color, and golden in this context is a brand. Okay? So how do we end up performing this? So let's go step by step and try to sort it out. So the first model is basically word representation. So in word representation, what you are trying to do is find a way to divide your string into smaller units of meaning, and for each one of those units of meaning, give it a numerical representation. And there are a lot of different ways to build this numeric representation, and most of them rely on embeddings. So you basically create embeddings around your words, and this is basically a really simple way to sort this out, is to say that embeddings are basically a numerical representation. It's a way to create numerical representations for the information that you have. In this case, for example, I have words, so I want to give it, for each word, a different numerical representation. And ideally, I want things which are used in similar contexts to be closer to each other. Okay, so what you end up would be something like this. So you have a vector for man, you have a vector for woman, and you could even do those interesting things of you could subtract one vector with another and then add it to something, to another word, for example, king, and you would end up with a similar representation for the meaning that you have here. So there are a lot of things that you could do with word embeddings, but the main idea is that when you apply things to a neural network, you want things that have similar meanings closer together in order to have a smaller error. So you would penalize more if the words are more far apart than the other ones. So you end up with having a word representation for your vocabulary. This is a really interesting topic, and it's really extensive. We ended up testing 3 different ways to build your embedding representation. So we basically, the way those models are trained, you give it a lot of text. So in Farfetch case, we could give for each product the long description. And then with the long description, you would say, okay, those words are used together. Okay, so they should be closer in the mathematical space. Those words are never used together. Okay, so they should be spread farther apart. So you would basically end up with a word representation, and those are different techniques. We ended up using fasttext. Fasttext is really cool because you can use embeddings not only for the words, but also for the characters for each word. So you could basically say that words that have similar characters and similar meaning would also be mapped in a similar mathematical space. This is extremely valuable, for example, in cases of misspellings. So you would, if someone ends up doing a misspelling, the word representation for that word would be extremely similar to the correct form of the word. So, and this would be like the first step. And the next steps are basically those 2 steps after are basically ways to give syntactic and grammatical information to the model. So in the part of speech tagging model, you are basically giving a syntactic representation for each word. So in this context, this word, which has this mathematical representation, will be classified as an adjective. And in this context, the word which is similar to this one will be classified as a proper noun. So you are basically saying, depending of the way that the things are in here, like in the similar way that we do it, different syntactic annotations are given depending of the full context of the query. So we basically train a machine learning system to give me the part of speech tagging for each word. So this model would basically say for each one of the words, what's the syntactic representation? And you can see that right here, you start to be able to distinguish those 2 words, because you know that in this case, this is an adjective, and this is already a proper noun. And proper nouns are normally used with brands, and adjectives are normally given to colors, for example, or attributes to nouns. So we ended up using this state-of-the-art architecture, inspired in the work of Chengzhou Ma. We ended up having a lot of annotated data. So for each long description that we have at Farfetch, we had a training set with the correct syntactic annotation for each word, and you trained a machine learning model to learn me that pattern. So we use the LSTM with the CRF layer, which is pretty state-of-the-art for this type of end-to-end sequence labeling tasks, and we had pretty good results. So right now, I'm able to have for each word a representation, and then I have a model that says what's the correct syntactic annotation for that word. After that, I have the dependency parsing. And what's a dependency parsing? Basically, a dependency parsing gives me the relationship between words. So I'm able to construct like a graph in which you can have the connections between words. So I would say that, for example, the word golden in here, it's closer to the word shoes. And I could say that this word, golden here, it's much closer to the word goose. And then all those words would be closer to shoes, and golden would also modify shoes. Okay? So the idea here is try to see what's the closest word in which the word is modifying. So you could even have annotations like this would be like an adjective modifying a noun. So this connection could have like a grammar name for linguistics. And the way this is done, you basically, it's a cool trick to apply this in machine learning. So you basically end up having just 3 operations, so shift, left, and right. And you are able to parse all those connections if they don't intersect with just those 3 operations. So you have a stack and you have a buffer at the beginning. And then you have a root, which says basically nothing. So it's the root of the sentence. And then each operation performs an operation that moves something either from the buffer or the stack or makes a word disappear. So the first operation is a shift. So you pass the word from the buffer to your stack. Then you perform another shift. So you pass again the word from the buffer to the stack. And then the fun begins with a left. So when you apply a left, you are saying that this word is modifying this one. So if this word is already modifying, you erase this word. So you end up, you erase this word because it's modifying shoes, and then you apply a shift. So the next word passes to the stack. Okay? So then it passes again to the stack, so another shift from the buffer to the stack. And then you apply a left connection. So the word on the right will be the parent word of the word on the left, and this word would end up disappearing again. And then you would perform a left operation, and then this word would end up, and then it would point towards the root, and the operation is over. So with this kind of approach, you are able to map it just with 3 operations, shift, left, and right. And you could also mount it as a machine learning system in which you receive your words. So you receive it here. It's this arrow right here. You receive the words. You receive the syntactic annotation, which also is information which is really important to help this system do the correct labeling. And then you perform the predict. So you predict what's the list of operations that I need to do with that sentence that I gave in the beginning. You can see that the maximum number of operations that you have here, it's double the amount of words that you have here. So this is constant. So this is constant as the double of operations that you have here, because those are the most that you can do. And we also disconstructed it this way in order to mount it again as a pretty similar system to this one. But in this case, you receive 4 and end up with 4. We receive 4, but you end up with 8. So, but we also use those 2 architectures and mount it in a really similar way to the previous one. Those purposes are really cool to understand a little bit better how those things are made. But those are mainly grammatical and syntactic information. So at the end here, I will have the words, the syntactic representation, and how the words connect to each other in a meaningful way, just using syntactic and grammatical information. And at the end, I have my named entity recognition, which is the most common tasks of all of this. And the main idea here is to, for each word, give a correct named entity. In our case, each named entity has a specific meaning. So, for example, for each product at Farfetch, I have a field called color. And then I can say, okay, when you search for something like this, you are going to match golden just against the field color, because if it's not in the field color, then we don't have anything golden, because the rest of matching it against categories, against long descriptions, don't make that much sense. And then you can say this, that this golden goose will be matched against brands. You don't want to match it against color or against category, because in this context, this is relevant if you search it against the brand, the list of brands. And the paper which we follow the architecture is pretty similar to this operation here, because the task is pretty much the same, but you have different information. So in here you have syntactic parts, syntactic part of speech tags, and in here you have named entities to tag. So to give you a bit of notion of scale of how many data that we use, we have a total of 91k unique words in this system, and we have 21.3 million annotated sentences to make this whole system work. And this is the live results on Farfetch website. So basically, if you search for "I want red and long dresses," and this is the current form, and this was the previous form. So you can see here, for example, you have "I want or wanted a." So the results have a really different quality, because in here you are saying on the new version, hey, look, red is a color, long is an attribute of a category, and the category is dresses. So in here, just show me long red dresses. And in here, you are matching against a whole bunch of fields. And the reason why I want red and long dresses don't show up any long and red dresses is because you are matching "I want," for example, in here, and "I want" in here, and "I want" in here. So you end up in a really strange list of products that don't necessarily mean what you are trying to look at. And we published our results on KDD. So if you guys want to check this out in a little bit more of detail, you can see our work here. And going a bit back to the main diagram that I showed up. So basically, looking at this diagram, we mainly work here. So I basically found a way to give more information to my query and then use it on the matching part. So I have a lot of data incoming at Farfetch each day. Each product is categorized, so I may know that a product is a dress or is I don't know, it's a bag or something. And then I store it somewhere. And then we found a way to enhance our query understanding. So we basically, for each query, were able to find a way to give more information to the query in order to have a better match between documents and queries. At Farfetch, we work also in a lot of different things right now. So, for example, we have specific teams working on this sort after. So basically, I want items that sell the most at the top, and I want items that don't have stock to the bottom. So you have a lot of optimization going on here. We also are trying a set of new things around this area, in which you are trying to do, instead of having like a named entity recognition here, in which you try to map it, but when you are trying to do this mapping, it still is keyword-based matching. So you are matching text against text. What we are trying to also do is try to match text against documents, but with neural networks. So you feed the neural network a query and a product, and it calculates automatically the score and gives the results. And these are mainly the research avenues that we are exploring at Farfetch. And with this, I conclude my presentation. If you guys have any doubts, feel free to answer. Yeah. Yeah, we use Elasticsearch for storing. Yeah, mainly at Farfetch, the main core is in .NET, Our AI applications, microservices are all developed in Python. And we have Elasticsearch. We also have some tricks. For example, those models take a lot of time to run. So we have simplified versions responding in real time, but we also have more complex versions which render this specific model, which are run as the cache. Not necessarily. For example, the first time you search for a query, the query may be processed, and the second time you answer, you have a cache. But you can also, we also have a smaller system that represents this one, in which answers like in real time for the first time. And in this case, one of the most important things when you are performing information retrieval is the time of response. So if it surpasses like 100 milliseconds, the experience is terrible, so the CTR goes down the hole. Yeah. Yeah. Okay, so yeah, let me just, okay. So, for example, each time that we have an interaction with our website, we register and we have a log and we have a big data lake with all the information. And then we have, for example, teams of analysts that say, oh, look, those queries aren't showing up any results, or those queries have a below average CTR that we didn't expect. So we are able like to track in some ways like where are we having least quality than we expect. In terms of, for example, recommendations, the challenge is pretty much it doesn't fit inside this team. So basically in here we just are retrieving products. When you are performing recommendations, you look at different, for example, I'm here, I look at the queries, and then given the query, I try to give the list of results. When I'm performing recommendations, I'm looking to the historic behavior of the user. I'm looking to similar things in which the user previously seen. I look, for example, where's my user in the cluster of users that I have. And then I also retrieve a list of products, but that's like a different pipeline than the search pipeline, let's just say. Yeah. Yeah. Yeah, we are in the process of replicating this. So basically, we did this as exploration mainly for English because it's easier to have the resources, the annotated data sets.